In this video, we are going to introduce the concept of a sequence. Now, a sequence is simply going to be an infinite list of numbers. Sometimes there will be a pattern to these numbers, sometimes there won't necessarily be a pattern. However, there are several different ways that we can define what a sequence is. The most typical notation that we'll have for a sequence is we'll use a set of brackets and a sub n, where the n is referring to an index. Typically, unless otherwise indicated, the start of the sequence will be when n is equal to 1, and it will go up one at a time until you get to infinity. So listing this as the actual list, this would be the first number of the sequence, followed by the second number of the sequence, followed by the third number of the sequence, followed by the fourth number of the sequence, and so forth and so on. So an example of one such sequence, I could ask you to do something like 2n as n goes from 1 to infinity. So plugging in n equals 1, we would get 2 times 1. That would be the first term. Plugging in n equals 2, we'd have 2 times 2. That'll be the second term. N equals 3 will give us the third term. N equals 4 will give us the fourth term, and so forth and so on. There are, of course, other ways that we could do something like this. We could take n divided by n plus 1, for example, and this time we could start at, say, n equals 3 and go up to infinity. So for n equals 3, we would have 3 over 3 plus 1. Then incrementing up 1 at a time, n equals 4 would give us 4 over 4 plus 1. Then n equals 5, that would be 5 over 5 plus 1, and so forth and so on. Now, this is when a sequence is well defined. There are also other ways that you can define sequences. Oh, hang on, let's see if I can spell. Recursively defined sequences. For recursively defined sequences, this is where new terms of the sequence are going to be put in terms of the previous terms of the sequence. There is a famous example that is known as the Fibonacci sequence. For the Fibonacci sequence, it is defined thusly. The first term is going to be 1. The second term is going to be 1. Any term beyond those is going to be the sum of the two previous terms. The way that we can say so is for example, the third term will be the second term plus the first term. The fourth term will be the third term plus the second term. So this will be for all n greater than or equal to 2. So if I wanted to actually list the numbers of the Fibonacci sequence, I would start by saying 1 and 1. To create the third term, I take the sum of the previous two. So 1 plus 1, that'll be 2. For the next term, 1 plus 2, that'll be 3. Then 2 plus 3, we get 5. 3 plus 5, we get 8. 5 plus 8, we get 13. And so forth, and so on, and so forth, and so on. There is a certain point where I like to stop writing the terms, and it's right here, because that happens to be my office number, assuming that I ever see my office again. #RIP. Now, when it comes to the Fibonacci sequence, it does have a very special property that if you take the limit as n goes to infinity of the ratio of consecutive terms, you actually wind up with a number. This number is known as the golden ratio. The golden ratio is equal to 1 plus the square root of 5 all over 2. The mathematical significance of this number is that it is considered to be the most aesthetically pleasing ratio in all of mathematics. If you have some time to do a Google search for the golden ratio, please take some time to do so. It's really fantastic. Now, with that in mind, some terms that are going to be important. A sequence converges. if the limit as n goes to infinity of a sub n exists. That is to say, you get one single finite value for it. Otherwise, the sequence diverges. Now, converges and diverges would be the verb form of these. We can also say that the sequence is convergent or is divergent. So, one example of each. On the previous page, we had defined the following sequence of 2n to be 2, 4, 6, 8, 10, etc. Now, if I were to consider the limit as n goes to infinity of 2n, I would get that this thing diverges toward infinity. So this sequence diverges because we don't wind up with a single finite value. Whereas on the previous page, when we had defined the sequence of n over n plus 1, starting at n equals 3, we wound up getting things like 3/4, 4/5, 5/6, 6/7, etc. If we were to consider the limit as n goes to infinity for this sequence, n over n plus 1, this can be evaluated through one use of L'Hopital's rule, and we differentiate the top and bottom with respect to n. Now, in this case, we did get one single finite value out of this, so this sequence converges. So, just some elementary terminology for you. More to come.